Welcome to this explainer. I am so incredibly excited to dive into a topic today that is literally shaping the future of human technology. Yet, it often flies completely under the radar. Today, we're going to completely shatter the illusion of what the word ceramics truly means in the 21st century. We're looking at ceramic engineering, the hidden powerhouse behind everything from modern aerospace and biomedical devices to advanced electronics.
Okay, let's dive right into this. What in the world do jet engines and artificial hips have in common? If you're scratching your head, hey, you're definitely not alone. On the surface, human biology and aerospace engineering couldn't be further apart, right? But at their core, the absolute most advanced versions of both rely entirely on the exact same category of engineered materials. And this brilliantly illustrates the massive shift in how we actually need to think about this field. When most people hear ceramics, they picture traditional applications: pottery, clay bricks, maybe a terracotta roof tile. And while that's historically accurate, today's ceramic engineering is totally focused on advanced technical ceramics. We're talking about silicon carbide, piezoelectrics, which are literally materials that generate electricity just from physical pressure, and bioceramics. These are non-metallic, inorganic materials processed at crazy high temperatures to achieve properties that metals and plastics simply cannot match. It's a whole different ballgame. Not just pots and pans, unveiling the high-tech reality. We're talking about the invisible backbone of modern high-tech industries. Without advanced ceramic engineering, semiconductor manufacturing just completely grinds to a halt. Energy storage breakthroughs, they stall out entirely. It's a highly specialized branch of materials science that is absolutely essential for technological progress in the modern world. Section 2, Science of Extreme Materials, a rigorous academic discipline. Look, to build materials that can survive a jet engine or live inside the human body for decades, you need an incredibly rigorous academic foundation. Ceramic engineering is the intense science of extreme materials. It requires a really deep understanding of crystal structures, phase diagrams, and how a material's microscopic structure dictates its macro-level physical properties. Just take a look at these B.Tech syllabus highlights pulled straight from premier academic institutions. Students in this field aren't just playing with clay, for sure. They are deep into heavy physics. We're talking thermodynamic potentials, understanding exactly how heat behaves at a molecular level, and the intricate mechanics of preventing fractures in extreme conditions. They even dive into cutting-edge fields like ceramic additive manufacturing, which is basically 3D printing, but with advanced composite materials. Now, what's really interesting here is that the real magic of ceramic engineering comes down to a process called sintering. This is how you take a raw powder and, through incredibly precise applications of temperature and atmospheric control, force the crystalline solids to bond at an atomic level. You are literally controlling defect chemistry and cellular diffusion to create incredibly resilient, hard materials out of almost nothing but powder and intense heat. It's wild. Section 3. Transforming aerospace and medicine, making the impossible possible. So where does all this intense science and academic rigor actually go? Well, it goes into making the impossible possible in high-stakes environments. Let's look at how these extreme materials are currently transforming both aerospace and medicine. In aerospace, materials are pushed to their absolute thermal and mechanical limits. Surprisingly to a lot of people, ceramic matrix composites, which are specialized blends of fibers and ceramics, are now absolutely essential for surviving the brutal thermal shock inside next-generation jet engine turbines. They provide superior thermal performance in extreme heat, where traditional metals would simply melt or warp. Engineers are even developing transparent ceramics that are strong enough to be used as armor and in advanced optical defense applications. How cool is that? Moving from the sky to the human body, the medical advances here are truly mind-blowing. We have bioinert ceramics, which are incredibly durable materials that the body's immune system won't reject, perfect for things like dental crowns or artificial hip joints. But then we have bioactive ceramics. These are actually engineered to interact with human tissue, actively promoting bone regeneration and even acting as targeted drug delivery systems, a real game changer for medicine. Section 4. Powering sustainable energy technologies, the green energy frontier. Beyond keeping planes in the air and healing the human body, perhaps the most urgent application for these materials is powering our sustainable energy future. Honestly, we just cannot build a clean energy green frontier without advanced ceramic components. The American Ceramic Society Bulletin actually sums this up beautifully. To quote them directly,
Ceramic and glass materials are ubiquitous in energy technologies because of their unique properties. And they're chosen precisely because they offer high temperature stability, unmatched wear and corrosion resistance, and incredible radiation tolerance. So the crucial point here is that our green energy breakthroughs rely entirely on these advanced ceramics. If we want next-generation lithium batteries, we absolutely need ceramic solid-state electrolytes. If we want high-efficiency fuel cells that don't degrade in dual-gas environments, we rely on ceramic interconnects that are specifically doped, which basically means they have intentional impurities added to boost their performance. Even safely immobilizing nuclear waste for the long term requires specialized glass and ceramic waste forms. This stuff is completely foundational to the planet's future. Section 5, Lucrative Career Opportunities, Engineering a Secure Future. Because ceramics are needed in literally everything from human bones to jet engines, the career opportunities here are incredibly diverse. The demand for these materials is skyrocketing, and naturally, the demand for the engineers who can conceptualize and manufacture them is surging right alongside it. Let's neatly map out these baskets of opportunity. Ceramic engineers basically act as true architects of innovation across a massive variety of industries. You could be a process engineer in the semiconductor industry working for giants like 3M or Corning. Or maybe you're a materials researcher in the biomedical sector for Saint-Gobain, or even a refractories engineer pushing aerospace limits with Kyocera or Corstech. The versatility of this degree is just astonishing, allowing professionals to pivot seamlessly between vastly different high-impact sectors over the course of a single career. And the compensation directly reflects that massive value. In the U.S., ceramic engineers are looking at salaries starting between $70,000 and $100,000, with senior researchers and managers easily pushing well past that six-figure mark. The industry absolutely pays a premium for this highly specialized knowledge. And it's a globally lucrative field, too. For experienced professionals in specialized sectors like aerospace, ceramics, or semiconductor manufacturing, in the Indian market, salary brackets reach 10 to 20 lakhs. It's a career path that offers immense intellectual challenge right alongside tremendous financial stability. Section 6. Forging your educational path. Steps to becoming an innovator. Clearly, the industry demand and financial rewards are there for the taking. But how do you actually get there? For the aspiring students tuning in right now, let's map out the actionable steps to forging your educational path into this exciting field. Let's break down exactly how this builds step by step. First, you've got to master the foundational sciences: chemistry, physics, and thermodynamics. Second, you transition into a specialized B.Tech or master's program in ceramic engineering or materials science. And third, you bridge all those academics into industry R&D or high-tech manufacturing roles. It's a very clear, structured progression. And you definitely don't have to look far for world-class education. There are premier institutions globally that provide exactly this rigorous training. In India, places like IIT BHU Varanasi, NIT Rourkela, and Anna University lead the pack. Internationally, you've got heavyweights like Alfred University in the US, the University of Manchester in the UK, and Aishan University in Germany. But remember, classroom learning is only half the equation here. Real-world experience matters immensely. The sources specifically highlight organizations like the Pacific Northwest National Laboratory, or PNLL, which offer applied internships that give students hands-on access to cutting-edge scientific instruments. Getting into the lab, working on real-world energy storage or nuclear waste form problems alongside actual professional researchers, well, that is what transforms a student into an industry-ready engineer. As we wrap up this explainer today, I want to leave you with this final, provocative thought. We are moving rapidly into a future defined by extreme temperatures, the absolute need for sustainable energy, and a push for much longer human lifespans. And ceramics are at the heart of all three. So, looking at the road ahead, what world-changing technology will you build as an architect of innovation? I really hope this has completely changed how you view this incredible field. Thank you so much for learning with me today, and keep exploring.